Okay. So please be aware that you're being recorded now. So we have here the review slides in front of us, which are wrongly titled, I just saw. So this is in essence material that was developed in 2019. So I think in general terms, so these are the general terms that were defined in the beginning. So we talked about the different types of variables. Make sure that you know how to distinguish those and how to categorize them in the various variable types. So again, you have numerical variables, you have categorical variables, you have continuous and discrete. So continuous are basically most of the variables that you essentially will be exposed to in the realm of data analysis. So these are basically variables that can take any value. You can further categorize them into interval and ratio variables, which wasn't done for this course. Then you have the discrete variables. These are, for example, counts would consider discrete variables in distinction to categorical variables, where you have regular categorical variables that basically have no ranking and no order, in contrast to ordinal variables that have some form of ranking contained in them. From there, you continue on into random assignment, which is random sampling. I would suggest to understand in principle why random sampling is important. How does it differ from random assignment? What is essentially the outcome of random assignment and random sample, where you basically get to the possibility to establish causality. Know that causality is only to be established from randomized trials where you minimize confounding to the fullest extent. Then you have observational studies with hopefully good generalizability, where you have those that do not have generalizability, where you in both cannot establish any causality. With no random sample, you cannot establish causality quite well. You will have confounding plaguing you with your interpretations. Understand the shapes of distributions. What does unimodal mean? How does a normal distribution look like? It's symmetric, unimodal, and bell-shaped. What other shapes can you think of? What shapes can you take on? Why is this important? What measures of central tendency, what measures of variability will you essentially using to describe your distributions and your data? Understand skewness. What does right and left skewed mean? Please don't mix up. So the tail tells the tail. That means like the direction in which the tail points is the direction in which the distribution is skewed. So when it's right skewed, it's actually positive skewed, whereas when it's left skewed, it's actually negatively skewed. Understand the various points of displaying distributions. So there are the histograms, as you see them here, with each of these bins indicating the count of entries having a certain value within these bins. Then you have the box whisker plot here. Know in approximate terms, or know exactly what the box whisker indicates. You have a median, you have a Q1 and a Q3, where Q1 is essentially the first quartile or 25th percentile, where Q3 is the third quartile with the 75th percentile. You have the whiskers. The whiskers have an upper whisker and a lower whisker, whereas the upper whisker is Q3 plus 1.5 times the IQR. The IQR is the range between Q1 and Q3. The lower range is Q1 minus 1.5 the IQR. Then you have a normal distribution. Understand the principal assumptions of a normal distribution. So it's symmetric, bell-shaped, and unimodal. If you have a notation like that, it means that N stands for normally distributed around a mean of mu and a sigma, a standard deviation of sigma. So this is a common notation that you will see in the common in the next following classes of biostatistics that you will be doing. So you essentially you have when you have a mu and a sigma given, so you have the actual Greek letters, you essentially need to think of population parameters. When you have here an X bar and S, or X bar in most terms, it can also be an M. So the notations differ a bit, but when it's not a Greek letter, it will indicate a sample. And in a sample, you don't speak about parameters, you speak about statistics. So it's population parameters and sample statistics. Understand how to standardize. Basically, you can every score on your normal distribution can be standardized by the computation of set scores, where basically you standardize the distance of each score from the mean by numbers of standard deviations as the distance, as the metric of distance. So basically, you can standardize every value, and you can, from the actually derived set score, you can also calculate back to the actual score. So this is important then later on for the set statistics. So the standard deviation will indicate those set scores. Standardized distributions do appear in the same shape, but basically the set score represents the values. You can do this then, and this is important. So you essentially can, using the set scores, you can actually, using the set score table or the norm dist function, you can characterize the number of population entries to the left of your set score. So when you have here a set score of -1, you have 15.87% of your population with values smaller than this set -1. So if you were to calculate, for example, everything that is greater than this -1, you would need to assume that the entire area on the curve here represents 100% or 1 as a proportion, and you're subtracting whatever is left from that set score. So these 15.87% from that 100%, that gives you everything that's greater than this set score. In the same fashion, you can calculate also values between two entries. So if you have, for example, let's say you want to know how much is between a set score of +1 as opposed to a set and between a set score of +1 and -1, you essentially calculate the area under the curve up until the +1, and you're subtracting the area under the curve smaller than -1. The difference between those both is essentially the area under the curve, or the probability and percentage between -1 and +1. So that way, essentially, you can quantify the percentage of a population, or the proportion of a population in between two values. And so this is very important to know. So this essentially we did in class. So this is done with the norm dist function. So if you calculate 1 minus norm dist, you essentially get everything greater than that set score that you have investigated here. So you can see. Good. Hi, Spresa. Just so you joined.
Hello.
Hello. Do you have any specific questions? I'm just walking through the review slides to kind of give my thoughts and emphasize what I find is important.
I don't have anything specific. I just kind of here to hear what you emphasize and try to focus on that.
Okay, sounds good. Sounds good. Okay, so same principle, essentially 1 minus norm as this gives you essentially everything that exceeds this value. If you want to calculate differences, you need to calculate, just as emphasized before, you need two set scores. You need the percentages between both. The difference, if you're subtracting the smaller one from the bigger one, essentially gives you the area in between. So that's the proportion of the population that falls between these 2 points. So please make sure to know that. So you can essentially calculate this in both directions. So if you retransform this formula, you basically get to calculate the x, knowing the set, the mean, and the sigma. So the mu and the sigma allows you to calculate the individual score. So this was the example we did in the context of the set score. Calculate this quite easily. Here's some examples. That's the 68, 95, 99.7 empirical rule. This empirical rule indicates that you basically have from -1 standard deviation, or -1 set score to +1 set score, you have 68% of your population. If you look at the proportion of the population between -2, set score of -2, and set score of +2, you capture 95% of the population. And 99% of the population falls between 3 standard deviations. It's called the empirical rule. Contingency tables is a way to summarize data for categorical variables. So these are essentially counts. And this essentially allows you to calculate all the risks and odd ratios, but also allows you to quantify probabilities in these groups. So we talked about that. Make sure that you also review this. I have this open already in the back because I wanted to make that point. Please understand how to calculate. And there's another, that was session 2, I believe. In session 2, essentially, you have a spreadsheet that allows you to calculate the exact probability. So you have a prevalence, a known prevalence, and you have a certain trial count. Know what the exact probabilities are for each of these success counts, and also understand cumulatively how to approach this. So if you want to have at least one individual, you need to have the probabilities for 1, 2, 3, and 4. So this is the inverse. This is 1 minus the exact probability of having no successes. So this is essentially 1 minus this exact count for 0. So make sure that you understand in principle how this can be employed. And I have put this little spreadsheet here. That was a question. I forget who asked the question, but I put together this spreadsheet to show how to calculate this and how to distinguish between at most and at least. So this is something I want to emphasize. And this is important that you will know how to approach this. So here are the examples. We have done this. We've also talked about the normal approximation. So we can approximate these binomial distribution and these prevalences under the assumption that you're drawing random samples and you will shape a normal distribution around the actual prevalence if you sample large enough samples repeatedly, randomly from the population. So you will get estimates of this prevalence based on the sample that you have sampled and the assessed prevalence within your sample. So you get estimates of the actual population prevalence, and therefore you can employ on these estimates essentially a distribution around a true prevalence in the population. So that's the idea. Basically, the same principle applies as you would employ for a normal distribution and a set statistic. So it's the same dynamic that employ. Comes with caveats because essentially you have only the possibility to do normal approximation if these criteria are met. So if n multiplied by 1 minus p or n multiplied by p both exceed 10 or are equal, greater equal 10. So there are some examples on the review slides. Really go back to these slides and make sure that you understand these examples. Like here was the example of the Facebook power users. Make sure that you know how to calculate those. Then you have the standard error of the mean. This was the context of the central limit theorem, where essentially you talked about this, the way you're basically relating the variability in a population. So we have a variability in the population, you have a standard deviation of the population given. You say, based on this variability, I can now estimate if I draw a large number of random samples, I get now estimates of the population mean, with each of these sample means being to some extent related to the population mean, because I'm randomly sampling from this population. But the larger the sample size is, the more closer that sample mean will be to my actual population mean. Meaning, as a consequence to that, my sample estimate and this mean of these randomly sampled means will be closer to the population mean, and it will show less variability as a consequence to that. Meaning, when your sample is larger, your resulting standard error of the mean here becomes smaller, because your estimate gets more accurately reflecting what population this was sampled from. And this is the knowledge that we essentially will then use, as we know, for the set statistic, and equally also in your normal approximation of the binomial sample proportions. So here you're using the normal approximation, you're using set statistic essentially to do hypothesis testing with proportions. Make sure that you have reviewed that, because that will allow you to also calculate 95% confidence intervals, not only for your continuous data, but also for the proportional data, for the binomial data. So, so this brings us to the next topic, which is essentially the confidence intervals. So essentially, you need to understand that there's a point estimate of your population mean. So you have a sample, you're calculating a sample mean. This sample mean is a point estimate of your population mean. So with the confidence interval, you create an interval within which you're 95% confident the population mean needs to be located in. There's only this 5% of type 1 error risk, just like in hypothesis testing. So this is calculated by essentially taking the X bar plus minus the critical set value, which is in a normal distribution, it's 1.96 for the tail of 2.5% to the right and 2.5% to the left, multiplied by the standard error of the mean. Aforementioned standard error of the mean, which is essentially the variability of your sample mean and your point estimates, your various point estimates from these randomly sampled and repeatedly sampled samples. That essentially varies around this mean of means, that essentially is your best point estimate for that population. So you add or you subtract this critical set that you're willing to accept as your quote unquote alpha, your type 1 error rate that you're willing to accept, multiplied by the standard error of the mean. And this is how you calculate the confidence interval. So essentially what that implies is that if you do repeated samples, 95 out of 100 samples will within this interval kind of capture that population mean. This is what this indicates. Only 5 will not capture your population mean. So this is also essentially, you can do hypothesis testing just with confidence intervals. So these 5% are identical to the alpha level that you accept as a level of significance, which can be 5%, doesn't have to be 5%. So you can also, particularly with large samples, for example, you would accept only smaller levels of significance. So you would basically, kind of reduce your acceptance level for a significant p-value. Also in this context, so when you think of the distinction between a 95 and a 90% versus a 99% confidence interval, understand in principle in what direction this needs to change. So when you have a 90% confidence interval, you're less certain that you will be able to quote unquote capture this population mean in your confidence interval, right? So this will essentially come with a smaller interval. So your set score that you're willing to accept is smaller. Whereas when you have a 99% confidence interval, your interval is actually wider than the 95% for a 95% confidence interval. So essentially in numerical term for 90% confidence interval, it's 1.65 as a confidence interval, whereas it's 2.58 for a 99% confidence interval. Because when you make the interval wider, you increase your confidence that you capture this population mean. So know the 6 steps of hypothesis testing. So here only 4 listed. So you would also include the characterization of the sample distribution as step 0, so to say. And essentially you have the decision of which alpha level you're willing to accept could be in separate steps. So there are various approaches to that. I think 5 steps, 4 steps here, 6 steps for some other books that I've seen. Then you have a null hypothesis, is claims that there's no difference between your sample mean and the population mean. And the alternative hypothesis claims there's a difference. So essentially what you do, you have your mean, and you calculate this mean from, you calculate the difference between your sample mean to the population mean. And then essentially what you do, you use the knowledge of the standard error of the mean to standardize this difference. And if this difference exceeds a certain value, you are willing to reject the null hypothesis. And this is 1.96 in the hypothesis. In a two-tailed test, you would take 1.96 with 2.5% on each side in a two-tailed test. So now when you are basically willing to accept the type 1 error, you are also willing to accept this at a percentage of a probability of 5%. That means that you're committing a type 1 error. So you're rejecting a null hypothesis, although the null hypothesis is true. That's a type 1 error. This is your alpha. A type 2 error is a failure to reject the null hypothesis, although the alternative hypothesis is true and the null hypothesis is wrong. If you do that, the resulting type 2 error is the so-called beta. So the correct decisions is rejecting a null hypothesis when the alternative hypothesis is true, and to fail to reject the null hypothesis when the null hypothesis is actually true. And this is the so-called power. So if you have a type 2 error and you have summing up here 100% probability, and you calculate 1 minus the type 2 error, you essentially calculate the power with 1 minus type 2 error, the beta. You don't want this to exceed. Usually it's in trial design, it's 10%. So, and the p-value is the probability of making type 1 errors. You basically you classify your p-values, and your p-values gives you essentially kind of a strength of your probability. So here, this is what I said as the statistical power. So Professor Johnson set it to 80%. In trial design, it's mostly 90%, it's slightly higher, but it can also be 80%. This will also guide you to essentially to set your sample size, because one way to essentially approach power is to increase your sample size, because as a consequence of that, you will get smaller margins on the standard error of the mean, and you will get more accurate estimates of your variability of those means. Further, you can also intensify your intervention, and you can increase the difference between both means. You can decrease the variability. That's a little trickier to do, and you can change your alpha. By that, you also will be more likely to see higher power. So then we have one sample t-test. The difference between the t-test is difference between a set test and a t-test is that for the set test, you have the standard deviation given from the population. For the t-test, you don't have the standard deviation given and you're estimating it from your sample. So the test statistic is calculated in the same fashion. You have your X bar from the sample, you subtract from that your population mean, and you again standardize your difference using the standard error of the mean. And then you're converting it with a z-score, with a t-score table to convert your statistic into the p-values. Confidence intervals are done in the same way. Don't confuse, please, the z-scores with the t-scores. Make sure that you understand that when you have a t-distribution, you need to use the t-value to estimate and to set the confidence interval. So when you ask for the calculation of the confidence interval, make sure that you know whether you're in a population on a normal distribution, on a set distribution, or you need to employ a t-distribution. So this is a distinction that is very important because you will have, with your varying degrees of freedom, different critical values for the calculation of your confidence interval. So then we have paired samples. Make sure that you recognize also in the t-distribution and t-test, in the realm of t-tests, that you understand whether this is a one sample t-test where you're comparing a sample mean to a population mean, or whether you have a paired sample where you have a before and after condition where you're comparing before and after and characterizing the differences between these two chronologically dependent values. Or you have an independent sample t-test where you have two individual sample population which you mean to compare against each other. These are important to be aware of and to distinguish between analyses. Degrees of freedom are calculated by the sample size -1. As you know, this is important because it affects a lot of aspects in the calculation of the independent sample t-test, but it also affects the calculation or estimation of the standard deviation. Confidence interval. So this is the confidence interval for your difference from a paired sample t-test. So essentially what you do is you characterize your differences according to the 95% confidence interval. What is important that if you characterize a difference with a 95% confidence interval, again, for a test statistic, you essentially, with a one sample set test, with a one sample t-test, and with a paired sample t-test, you correct. It's also for the independent sample t-test. The question is just what is the difference? What is the difference that you're looking at? If the difference is characterized with a 95% confidence interval, make sure that you know that if this is characterized with a 95% confidence interval, if this confidence interval does not contain the zero, you are basically looking at a difference that is not, that is essentially not containing the population mean. That means that automatically, if both are greater than zero or both are smaller than zero, you have a significant difference because the 95% confidence, where the 5% that is subtracted from 100%, that's your alpha. So make sure that you're aware of that you recognize and understand the intersections between hypothesis testing and the 95% confidence interval. And with independent samples, you're comparing two separate groups. They're not paired samples at this point, so there's no chronological dependency, and both of these populations are independent from each other. So make sure a lot of importance and a lot of weight is essentially to recognize which tests do you need to employ on this research question or on this question that you have at hand. That's really what's most important here. It's calculated different. So for independent samples, you need to adequately distribute your standard error of the means. And you're basically doing that because both of these sample populations may be different in size. So they may have different sample sizes. So that's why you create here a pooled standard error of the mean, pooling first the standard deviation, allocating them according to their size and giving them a weight according to their size. And then basically you use this pooled standard error of the mean for calculation of your t-stat. And this again, you convert them using a t-score table or software to a p-value that will allow you then to do hypothesis testing. So that's a very nice slide. I also recommend reviewing this slide. So it's important to kind of understand how are the standard errors calculated, how do you define the degrees of freedom, and also that the degrees of freedom here are different because you have two independent groups. So then sample size per group, so you can calculate with the effect sizes, you can calculate the sample sizes that you need to achieve a certain power. This follows a certain formula that is dependent on sample size and the alpha and the difference in the intervention. As said before, you can achieve this power by increasing the sample size, decreasing the standard deviation of the sample, which is a little harder to do. Then you can increase the alpha, which you don't want to do because you also increase your type 1 error rate, and what you accept is your type 1 error rate. Or you can increase your effect size. And that's also sometimes hard to do because that implies that you need to increase the intensity of your intervention, which in many cases, as you can imagine, you can't really do. So then we have the 2x2 tables. Please know how to calculate relative risk and absolute risks and how to distinguish between all these relative markers of risk. That's also quite important to know. Then you have the odds ratios. Understand the differences between an odds ratio and the risk ratio. Although they have some comparability, they also are distinctly different conceptually. That's the one sample t-test. So we talked about this before. That's the set statistics. We talked about that. Understand the chi-squared. When do you use the chi-squared? What is the interpretation of the chi-squared? So it's really a chi-squared is only establishing an association, comparing an expected count to an observed count. And if you find such an association, you need to then look specifically on what causes this difference and where's the difference. So there's post-hoc testing with the chi-squared table that essentially brings it then further, but essentially with a chi-squared, all you do, you calculate the differences and you sum up the differences as a function of the expected values, and you create a chi-squared value that you're comparing then to a chi-squared distribution that is essentially a unimodal right-skewed distribution with a critical value that you essentially chose according to the degrees of freedom that includes the number of rows and the number of columns. And based on this critical value, you will then reject or not reject your null hypothesis, which is that there's no association between row and column variables, and these two variables that you have depicted in your contingency table. So make sure that you really had a look at this. Then we have correlation. I think this is rather on the simpler side. So you're basically calculating deviations on the x-axis divided by the standard deviation on the x-axis. The product of this deviation to the deviation on the y-axis gives you a sum of squares, and this sum of squares you're dividing then by your degrees of freedom in your correlation. So it is a value from -1 to +1. Please make sure that you understand that the strength is independent of the size, meaning that a very small value, which is closer to -1, is as strong as the corresponding positive value. So this is not an R squared, it's the squared. correlation coefficient. Understand regression analysis, simple and linear, and particularly the interpretation of this. Understand how to, this is also, I'm flagging this, understand how these tables are to be interpreted. What do the coefficient mean? What does a multiple linear regression with an explanatory variable? What does this basically mean when you have a table? What does each individual component mean? These linear predictors that you have, the systematic component, this always means that when you have a slope of this function, that the slope indicates the change of the y variable, of the dependent variable, with a change of 1 on the independent variable on the x-axis. So when you have here, for example, blood pressure, or you have age, let's do age on the x-axis, and you have here an increase of 1 year, you have a certain increase of blood pressure with an increase of 1 year. So this is very important, this dynamic to understand. So the simplest model is here with an intercept, the beta 0, beta 1 plus an error term. So this basically is in a simple linear regression consistent with a linear equation. So the equation for a linear function of a line, which basically has an intercept, and the intercept is where this function, this least square function, crosses the y-axis at an x value of 0, whereas the slope indicates, so the slope is here, the b1 or the beta 1, and this essentially is here this increase with 1 unit on the x-axis. The error term is essentially here contained somewhere in these residuals, in these squared deviations from the linear function. So, but this is something that you do in the next class of biostatistics. You can also calculate based on the correlation coefficient. You can calculate both the slope and the intercept, and this essentially is also what will be in more detail discussed in the next classes. You have then predictive and explanatory approaches that essentially you predict values based on the relationship between dependent and independent variable, whereas explanatory models are only assessing the impact of changes of an independent variable on a dependent variable. So this is really more hypothesis generating rather than an actual prediction. And this is also where you then essentially move already. So this is a depiction of the residuals. So basically, this standard error around this function will basically give you the t-score, whether this t-score is actually a significant slope, a significant intercept. Then you slowly understand directed acyclic graphs. So how actually confounder are being associated with both disease and exposure. With here, for example, is BMI and CVD confounded by age. So here age would hypothetically be a classical confounder, and this needs to be quote unquote adjusted for. So it's quite a there was also a question of one of your colleagues, what is adjustment? So this is basically what you're trying to kind of remove in a model based on that knowledge from your sample. So you would essentially, your coefficients are essentially representing the dynamics within that sample. So predictive models cannot be always employed in the same fashion in different populations. This is also where replication is a very important aspect of observational research and epidemiological research. And then lastly, you have logistic regression, where you are converting your probability to odds, to log odds, to essentially be able to describe exactly this function, this sigmoid function. And you're doing that essentially to still be able to employ linear predictors in your model and use the same model dynamics that you have had with multiple regression, but you're converting your odds ratio as an outcome into a logit function. And by converting it in the logit function, you're converting your log odds by exponentiation into an odds ratio. And this basically is here where you have a linear part in between, but you're reshaping it in a logit function, and by that you basically can transform your linear predictor that goes from minus infinity to plus infinity, with 0 being no effect. You can convert it, and you can convert it into an odds ratio that then basically gives you the possibility to estimate the odds for each individual subject and for your population per se. So important is to know when to use logistic regression, and this is basically which is here a binary outcome. So this is success or failure. This can be hospitalization, yes, no. This can be death, yes, no. It's important to keep in mind that this has, of course, assumptions, and one of the major assumptions is that it's a consistent risk over the entire period of time, and that this risk is not changing by loss to follow-up, for example, where individuals are dropping out. All right, so this is logistic regression. So this is a quick characterization of all these slides. It's a lot of slides and it's a bit of material. It's then also not as much material, but it is a comprehensive kind of material to understand. So, all right, are there questions? Anything in particular that I could explain at this point?
The slide that was on the exact number of successes for a certain number of trials in Excel.
Yeah.
Could you please go to that slide? I think it was one of the earlier slides.
This one?
Yeah.
No. Yes.
So for that one, what command would we have to give to calculate the exact number of successes?
Well, this is your binom dist, right? You remember that formula from the lab. So you essentially give it a binom dist. You have here a number of successes that you're interested in, which is here our B5. So we're interested in 0 successes. We have a B2, which is our trial. So this is the number of trials. Then we have a probability which we're expecting to be 10%. So this is 0.1. And the cumulative option would be false. This gives you the exact probability of 0 events to happen with a known prevalence and known number of trials. So it's binom dist. I have posted this Excel spreadsheet in the discussion board.
Oh, okay, great, great.
Yes.
The discussion board for that week.
Yes. That was a question of one of your colleagues, and there was a back and forth explanation, and I posted on the Excel spreadsheet, which is essentially outlines exactly that.
Oh, okay, great. Yeah,
Yeah.
I was just looking for the commands. Thank you so much.
You're welcome. No problem. Any other questions? So don't be too nervous. You have ample of time. You have a couple of challenging questions, but it's overall it's a very straightforward quiz that essentially asks you those questions that we've discussed now over the last, what was it, like 2.5 months, and I'm sure you're gonna do well. Don't worry. Just make sure you go through the slides. You maybe rewatch some of the lectures. Make sure you're comfortable with the material. In case you have any further questions, reach out on the discussion board, write me emails. I will ask you to post them to the discussion board because I want exactly this conversation to happen, but and I want everybody in the class to benefit from it. But I'd be happy to make myself available in case there are a couple of questions that are coming up now. We can have another quick check-in session. Happy to do that. And I'm sure you're gonna do great. So don't be too concerned about it.
I just want to ask the question, even though you might have already answered it. And what would you say it's enough to just study all the quizzes and just review the main labs? Like, is there any particular like chunk of those, like, I'm assuming labs like the last like 3 are probably what heavier, or is it like all pretty much equally represented on the test, like as far as the weeks go?
Yes, it's quite equally distributed. So I highly recommend to learn all lectures. So I think you will get questions from each of those portions. So
Okay,
there's not really a weight. So
okay, cool, thanks.
sure. All right, if no further questions at this point, I think we can conclude for today. If any further questions, please go to the discussion board, shoot me emails, let's have another conversation. Again, if there's a need or a wish for another check-in session, happy to do that sometimes early next week. If not, have a good night and let's talk soon.
Good night, thank you.
Thank you.
Good night, you're welcome.
Thank you.
Bye. You're welcome.